Hello, dear subscribers and guests of the channel. Since ancient times, people have been attracted to space and distant stars. We're talking about how the star system we live in works, which planets revolve around the sun, what is an interplanetary space, and other interesting information about our solar system. Once upon a time, the concept of the universe was associated only with the solar system. Now we know that it is tiny even on the scale of our galaxy, and the universe stretches much further than we can imagine. Nevertheless, the solar system is our piece of space, the only area where we can move, which we can study with satellites, and not just observe with a telescope. The solar system is a planetary system that includes a central star, the Sun, and all natural space objects in heliocentric orbits. It was formed as a result of gravitational compression of a gas and dust cloud about 4.57 billion years ago. The total mass of the solar system is about 1.001 per million. Most of it falls on the Sun. The remaining part is almost entirely contained in 8 distant planets with orbits close to circular, lying almost in the same plane, the plane of the ecliptic. Because of this, there is a contradictory distribution of angular momentum between the Sun and the planets, the so-called moment problem. Only 2% of the total angular momentum of the system falls on the Sun, whose mass is 740 times the total mass of the planets, and the remaining 98% is 0.001 of the total mass of the solar system. The 4 planets closest to the Sun, called the terrestrial planets, Mercury, Venus, Earth, and Mars, consist mainly of silicates and metals. The 4 planets more distant from the Sun, called giants Jupiter, Saturn, Uranus, and Neptune, are much more massive than the terrestrial planets. The largest giant planets of the solar system, Jupiter and Saturn, consist mainly of hydrogen and helium, and therefore belong to the gas giants. The 4 planets closest to the Sun, called the terrestrial planets, Mercury, Venus, Earth, and Mars, consist mainly of silicates and metals. The 4 planets more distant from the Sun, called giant planets Jupiter, Saturn, Uranus, and Neptune, are much more massive than the terrestrial planets. The largest giant planets of the solar system, Jupiter and Saturn, consist mainly of hydrogen and helium, and therefore belong to the gas giants. The smaller giant planets Uranus and Neptune, in addition to hydrogen and helium, mainly contain water, methane, and ammonia. Such planets are allocated to a separate class of gas giants, the ice giants. -1 of the 8 planets, and for dwarf planets, have natural satellites. Jupiter, Saturn, Uranus, and Neptune are surrounded by rings of dust and other particles. There are 2 regions in the solar system filled with small bodies. The asteroid belt, located between Mars and Jupiter, is similar in composition to Earth. There are 2 regions in the solar system filled with small bodies. The asteroid belt, located between Mars and Jupiter, is similar in composition to the terrestrial planets because it consists of silicates and metals. The largest objects in the asteroid belt are the dwarf planet series and the asteroids Pallas, Vesta, and Hygiea. Beyond the orbit of Neptune are trans-Neptunian objects consisting of frozen water, ammonia, and methane, the largest of which are Pluto, Haumea, Makemake, Quaver, Orc, Eris, and Sedna. There are other populations of small bodies in the solar system, such as planetary quasi-satellites and Trojans. There are other populations of small bodies in the solar system, such as planetary quasi-satellites and Trojans, near-Earth asteroids, centaurs, Damocloids, as well as comets, meteoroids, and cosmic dust moving in outer space. Through the system, the solar wind, a stream of plasma from the Sun, creates a bubble in the interstellar medium called the heliosphere, which extends to the edge of the scattered disk. The hypothetical Oort cloud, which serves as the source of long-period comets, may extend over a distance of about 1,000 times greater than the heliosphere. The solar system is part of the structure of the Milky Way galaxy. The central object of the solar system is the Sun, a main sequence star of spectral class G2V, a yellow dwarf. The Sun accounts for the vast majority of the total mass of the system, about 99.866%. It holds the planets and other bodies belonging to the solar system by its gravity. The 4 largest objects, the gas giants, account for 99% of the remaining mass, with Jupiter and Saturn accounting for most of it, about 90%. Most large objects orbiting the Sun move in almost the same plane, called the ecliptic plane. At the same time, comets and Kuiper belt objects often have large angles of inclination to this plane. All planets and most other objects revolve around the Sun in the same direction, as the Sun rotates counterclockwise when viewed from the north pole of the Sun. There are exceptions, such as Halley's Comet. Mercury has the highest angular velocity. It manages to complete a complete revolution around the Sun in just 88 Earth days. And for the most distant planet, Neptune, the rotation period is 165 Earth years. Most of the planets rotate on their axis in the same direction as they orbit the Sun. The exceptions are Venus and Uranus rotates almost lying on its side. The tilt of the axis is about 90. A special device, tellurium, is used to visually demonstrate rotation. Many models of the solar system conventionally show the orbits of planets at regular intervals, but in reality, with few exceptions, the farther a planet or belt is from the Sun, the greater the distance between its orbit and the orbit of the previous object. For example, Venus is approximately 0.330 further from the Sun than Mercury, while Saturn is 4.30 further from Jupiter, and Neptune is 10.50 further from Uranus. There have been attempts to deduce correlations between orbital distances, for example, the Titius-Bode rule, but none of the theories has become generally accepted. The orbits of objects around the Sun are described by Kepler's laws. According to them, each object rotates along an ellipse with the Sun at one of its foci. Objects closer to the Sun with a smaller semi-major axis have a higher angular velocity of rotation, so the rotation period year is shorter. In an elliptical orbit, an object's distance from the Sun varies throughout its year. The point of an object's orbit closest to the Sun is called the perihelion, and the furthest is called the aphelion. Each object moves fastest at its perihelion and slowest at its aphelion. The orbits of the planets are close to a circle, but many comets, asteroids, and Kuiper belt objects have highly elongated elliptical orbits. Most of the planets in the solar system have their own subordinate systems. Many are surrounded by moons, some of which are larger than Mercury. Most large satellites are in synchronous rotation, with one side constantly facing the planet. The 4 largest gas giant planets also have rings, thin bands of tiny particles orbiting in very close orbits, almost in unison. Terminology. Sometimes the solar system is divided into regions. The inner part of the solar system includes for terrestrial planets and an asteroid belt. The outer part begins outside the asteroid belt and includes for gas giants. Planets inside the asteroid belt are sometimes referred to as inner planets and outside the belt as outer planets. However, sometimes these terms are used for the lower inside the Earth's orbit and upper outside the Earth's orbit planets, respectively. After the discovery of the Kuiper belt, the most remote part of the solar system is considered to be the region consisting of objects located further than Neptune. All objects of the solar system orbiting the Sun are officially divided into 3 categories: planets, dwarf planets, and small bodies of the solar system. A planet is any body in orbit around the Sun that has turned out to be massive enough to acquire a spherical shape, but not massive enough to start thermonuclear fusion, and has managed to clear the vicinity of its orbit of planetesimals. According to this definition, there are 8 known planets in the solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Pluto, which was considered a planet until 2006, does not meet this definition because it has not cleared its orbit of the surrounding Kuiper belt objects. A dwarf planet is a celestial body orbiting the Sun. It is massive enough to maintain a close rounded shape under the influence of its own gravitational forces. But it has not cleared the space of its orbit of planetesimals and is not a satellite of the planet. By this definition, the solar system has 5 recognized dwarf planets: Ceres, Pluto, Haumea, Makemake, and Eris. In the future, other objects may be classified as dwarf planets, such as Sedna, Orcus, and Quaver. Dwarf planets whose orbits are located in the region of trans-Neptunian objects are called Plutoids. The remaining objects orbiting the Sun are small bodies of the solar system. The terms gas, ice, and rock are used to describe various classes of substances found throughout the solar system. The stone is used to describe compounds with high condensation or melting temperatures that remained in a protoplanetary nebula in a solid state under almost all conditions. Stone compounds typically include silicates and metals such as iron and nickel. They predominate in the inner solar system, forming most of the terrestrial planets and asteroids. Gases are substances with extremely low melting points and high saturated vapor pressure, such as molecular hydrogen, helium, and neon, which have always been in a gaseous state in the nebula. They dominate the middle part of the solar system, making up most of Jupiter and Saturn. Ices of substances such as water, methane, ammonia, hydrogen sulfide, and carbon dioxide have melting points of up to several hundred Kelvin, while their thermodynamic phase depends on ambient pressure and temperature. They can occur as ices, liquids, or gases in various regions of the solar system, while in the nebula they were in the solid or gas phase. Most of the moons of the giant planets contain icy substances. They also make up most of Uranus and Neptune, the so-called ice giants, and numerous small objects located beyond the orbit of Neptune. Gases and ices are collectively classified as volatile substances. The Sun is the star of the solar system and its main component. Its mass 330 to 1,900 Earth masses is large enough to support a thermonuclear reaction in its interior, which releases a large amount of energy, radiated into space, mainly in the form of electromagnetic radiation, the maximum of which falls in the wavelength range of 400 to 700 nanometers, corresponding to visible light. According to the stellar classification, the Sun is a typical yellow dwarf of the G2 class. This name may be misleading, as compared to most of the stars in our galaxy, the Sun is a fairly large and bright star. The class of a star is determined by its position on the Hertzsprung-Russell diagram, which shows the relationship between the brightness of stars and their surface temperature. Usually, hotter stars are brighter. Most of the stars are located on the so-called main sequence of this diagram. The Sun is located approximately in the middle of this sequence. Stars that are brighter and hotter than the Sun are relatively rare, while dimmer and cooler stars, red dwarfs, are common, accounting for 85% of the stars in the galaxy. The position of the Sun on the main sequence shows that it has not yet exhausted its supply of hydrogen for nuclear fusion and is approximately in the middle of its evolution. Now the Sun is gradually becoming brighter. At earlier stages of its development, its brightness was only 70% of today's. The Sun is a type I star of the stellar population. It was formed at a relatively late stage in the development of the universe and is therefore characterized by a high content of elements heavier than hydrogen and helium. In astronomy, it is customary to call such elements metals. Than older type E stars. Elements heavier than hydrogen and helium are formed in the cores of the first stars, so before the universe could be enriched with these elements, the first generation of stars had to pass. The oldest stars contain few metals, while younger stars contain more of them. It is assumed that high metallicity was extremely important for the formation of a planetary system in the Sun, because planets are formed by accretion of metals. The interplanetary environment. The heliospheric current layer. Along with light, the Sun emits a continuous stream of charged particles, plasma, known as the solar wind. This stream of particles propagates at a speed of about 1.5 million kilometers per hour, filling the solar region and creating a kind of analog of the planetary atmosphere, heliosphere, which is located at a distance of at least 100 km from the Sun. It is known as the interplanetary medium. Manifestations of activity on the surface of the Sun, such as solar flares and coronal mass ejections, disturb the heliosphere, generating space weather. The largest structure within the heliosphere is the heliospheric current layer, a spiral surface created by the action of the rotating magnetic field of the Sun on the interplanetary medium. The Earth's magnetic field prevents the solar wind from blowing up the Earth's atmosphere. Venus and Mars do not have a magnetic field, and as a result, the solar wind gradually blows their atmospheres into space. Coronal mass ejections and similar phenomena change the magnetic field and carry out a huge amount of matter from the surface of the Sun, about 109 to 10 tons per hour. Interacting with the Earth's magnetic field, this substance gets mainly into the upper circumpolar layers of the Earth's atmosphere, where auroras arise from such interaction, which are most often observed near the magnetic poles. Cosmic rays originate from outside the solar system. The heliosphere and, to a lesser extent, the planetary magnetic fields partially protect the solar system from external influences. Both the density of cosmic rays in the interstellar medium and the strength of the Sun's magnetic field change over time, so the level of cosmic radiation in the solar system is unstable, although the magnitude of the deviations is not reliably known. The interplanetary medium is the site of the formation of at least two disk-like regions of cosmic dust. The first, the zodiacal dust cloud, is located in the inner solar system and is the reason why the zodiacal light appears. It probably arose due to collisions within the asteroid belt caused by interactions with planets. The second region extends from about 10 to 40 and probably arose after similar collisions between objects within the Kuiper belt. The question of exactly where the solar system ends and interstellar space begins is ambiguous. Two factors are key in determining them: the solar wind and solar gravity. The outer boundary of the solar wind is the heliopause, beyond which the solar wind and interstellar matter mix, mutually dissolving. The heliopause is located about 4 times farther than Pluto and is considered the beginning of the interstellar medium. However, it is assumed that the area in which the Sun's gravity prevails over the galactic one, the Hill sphere, extends 1,000 times further. The heliosphere. The interstellar medium in the vicinity of the solar system is heterogeneous. Observations show that the Sun is moving at a speed of about 25 kilometers per second through the local interstellar cloud and may leave it within the next 10,000 years. The solar wind plays an important role in the interaction of the solar system with interstellar matter. Our planetary system exists in an extremely rarefied atmosphere of the solar wind, a stream of charged particles, mainly hydrogen and helium plasma, flowing out of the solar corona at great speed. The average speed of the solar wind observed on Earth is 450 kilometers per second. This velocity exceeds the velocity of propagation of magnetohydrodynamic waves. Therefore, when interacting with obstacles, the plasma of the solar wind behaves similarly to a supersonic gas flow. As we move away from the Sun, the density of the solar wind weakens, and the moment comes when it is no longer able to contain the pressure of interstellar matter. During the collision, several transition regions are formed. At first, the solar wind slows down, becomes denser, warmer, and more turbulent. The moment of this transition is called the boundary of the shock wave, English, termination shock, and is located at a distance of about 85 to 95 from the Sun, according to data obtained from the Voyager 1 and Voyager 2 space stations, which crossed this boundary in December 2004 and August 2007. After about 40 more, the solar wind collides with interstellar matter and finally stops. This boundary separating the interstellar medium from the matter of the solar system is called the heliopause. In shape, it looks like a bubble stretched out in the opposite direction to the movement of the Sun. The region of space bounded by the heliopause is called the heliosphere. According to the Voyager spacecraft, the shock wave from the south side turned out to be closer than from the north, 73 and 85 astronomical units, respectively. The exact reasons for this are still unknown. According to the first assumptions, the asymmetry of the heliopause may be caused by the action of ultra-weak magnetic fields in the interstellar space of the galaxy. On the other side of the heliopause, at a distance of about 230 from the Sun, along the bow shock, the interstellar matter impinging on the solar system decelerates from cosmic velocities. No spacecraft has yet emerged from the heliopause, so it is impossible to know for sure the conditions in the local interstellar cloud. Voyagers are expected to go through the heliopause sometime between 2014 and 2027 and provide valuable data on radiation levels and solar wind. It is not clear enough how well the heliosphere protects the solar system from cosmic rays. A NASA-funded team has developed the Vision mission concept, sending a probe to the edge of the heliosphere. In June 2011, it was announced that, thanks to Voyager's research, it became known that the magnetic field at the edge of the solar system has a foam-like structure. This is due to the fact that magnetized matter and small space objects form local magnetic fields, which can be compared to bubbles. The solar system remains a small piece of space available for our direct exploration. It is easier to obtain data on the development of the solar system using automatic stations and robots. And yet, humanity is still at the very beginning of the journey of space exploration. See you among the stars. Watch my channel and subscribe. You will learn a lot of new and interesting things. Click on the bell to be the first to watch new videos on the channel.